Oh, sorry, you just caught me catching up on the latest talk radio on the AM broadcast band. And I don't know when the last time you listened to AM was. I certainly haven't listened to it for a while. But the basic idea is that there's a big radio transmitter, it has a radio wave. It does something called modulation to it, and amplitude modulates it. That radio wave travels all the way down to your AM receiver, and then it's demodulated so you hear sound out of it. Now, for our purposes of audio synthesis, we don't need to worry about radio waves. We don't need to worry about a big transmitter. In fact, we don't need to worry about demodulation of it to listen to it. Instead, we're just interested in the modulation, which can make some very interesting sounds. So for that matter, what is modulation? Modulation is when you take a carrier signal, like this, which I've drawn at the top here, and you change its shape with a modulating signal. And so the shape of the resulting waveform comes out looking different. This is an amplitude modulated signal. So you see down here it's a very quiet amplitude, then it gets loud, then it gets quieter, then it gets loud again. And that's how you do amplitude modulation. Take this carrier, take this modulating signal, and you combine them with the modulation to get something like that. Now, this might be a bit of a dense video, and I apologize for that. But if you bear with me on the coding and the math, what we'll learn is a way to make some really interesting sounds out of our audio synthesizer. What this is the basic math behind it. We're going to have a carrier, I'll just call it carrier T, which will be that carrier I was showing you. We have the carrier, which is at the top. Then we have the modulator, which is at the bottom. And then we're going to have AC, which is the amplitude of the carrier. And this is not the amplitude that the carrier is at after it's modulated, it's just before. We have Ka, which is the amplitude sensitivity of the carrier. And then out of all that, we get this math equation, and I'll breeze through it here. I'll show it to you more in the code. Of our resulting modulated waveform will be the amplitude of the carrier multiplied by the quantity of 1 plus the amplitude sensitivity times the modulating waveform. And then all that multiplied by the carrier itself. So we're going to look at that. First, what we'll do is we'll code up something that just is a very, very simple modulation with amplitude, and then we'll go ahead and incorporate the slightly more complex amplitude sensitivity, and we'll figure out how that affects our final modulated signal. Before we begin with the amplitude modulation, let's go ahead and review just making a simple sine wave, and then we'll build on that with some modulation. So first we're going to need to import some libraries. We'll calculate the sine wave, then we'll write a wave file out. It's a file so we can hear it and look at it in Audacity and so forth. Let's go ahead and import the library. So we're going to calculate with NumPy. Then from scipy.io wave file we'll import write. And what we're doing with write is that function will allow us to write a wave file. So that's simple enough. Let's continue with the calculation. Oh, oops, I forgot. Before we actually calculate the waveform, we're going to need to find the properties of the wave. This will be our samples per second of 44,100. And I'm going to call it carrier hertz this time because instead of just having one frequency of our sine wave like we did in our first video, we're going to have two frequencies to be concerned with. One is going to be the carrier, the other is going to be the modulating signal. So I'll call it carrier hertz. Good old A440 there. Then a duration in seconds. I'm going to say 10 seconds. Normally I wouldn't want to listen to a sine wave beat for 10 seconds, but as soon as we start playing around with AM modulation, we'll need more of a time frame to listen to the results. Now we can actually calculate the sine wave. So we're going to say we're going to grab our samples, which I'll call the T samples. So this is going to make the NumPy range of every for having an integer for every sample we're going to need to calculate. I call it the carrier. And then this line goes ahead and calculates just for a simple sine wave. And it's going to be at the carrier hertz frequency. We're going to attenuate the waveform to 30% of its default value. And the reason I attenuated it is because everything that's going to happen to the waveform can be very loud. And I'm going to make integers. Oops, I made a little bug. Okay, then we're going to make integers out of the waveform so we can make the wave file for it. So we have our sample rate of 44,100, 16 bits. That's where that 32,767 comes from. And finally, on a lonely line by itself, we're going to write our simple sine wave. I need a body double for typing. We're going to output our final waveform. So just to review what we did here, we grabbed our needed libraries, NumPy, which will do our math calculations. Write is the function here, which will write the file. We defined our samples per second, our carrier hertz, and our duration in seconds as 44,100, 440, and 10 seconds respectively. And then we define an integer for every sample we need NumPy to calculate. Then we go through NumPy and have it vectorize an operation to calculate a waveform. So we don't need to actually do a for loop here. And it's just 2 times pi times the carrier hertz times number of samples. Okay, so NumPy is expanding this t samples in here so that it calculates every sample that we need, and then divide that all by samples per second. And then once again we use NumPy to just broadcast an attenuation of 0.3 across the whole waveform that we just calculated, and that's so that we don't get a loud blast when we actually play the sound file. And then we make integers out of the actual carrier wave we calculated, and that's just making an int16 array for 16 bits per sample along 44,100 samples per second. Finally, we use the write function, which we imported up here, to write out simple sine.wave at our samples per second with our integers that we just created. Let's listen to what we've got now. There. Now I'm going to go ahead and open up the wave file using QuickTime Player. Obviously, if you're on Windows or Linux or something else, just open it up in any player that can take a wave file. If it's a sound program, it can handle a wave. And now for the moment of truth. As you can see, I turned the sound down when I played that because that was quite loud. There is how we created our sine wave. And that sine wave will be our carrier wave. I went ahead and made another directory for step 2am, which has the file amplitude modulator.py. And here it is. It's the same thing. I'm going ahead and copying between the directories so we have the same file, but we keep changing it to add features so you can always see how we're building it up. I've opened up Audacity so we can take a quick look at our sine wave. And there's plenty of tutorials on Audacity, so I'm not going to go into much of what I'm doing here, except I'm just going to import my audio that we just made, the simple sine, make a copy. And as you see here, just zoomed out, it just looks like this blob of the same thing, which in fact it is. And there's the sine wave, as promised. So notice how its amplitude is constant, and notice how its frequency is constant. So the whole goal of modulation is going to be to change properties of this waveform so that we get a more interesting sound than just a constant beep. Another thing to note before we dive out of here and flip back to the editor to keep working is that we can see that the peak amplitude here is between positive 0.3 and negative 0.3. And that's because of our attenuation that we did right here. So it wouldn't be a blast of sound coming out of the speaker. So just a reminder about where we're going before we do it. We're just going to implement this equation right here inside of code, and we'll see how it works out. So we're going to start with the file that we just made, but instead of just simply making the sine wave, we're going to go ahead and modulate it. All right, so modulate the carrier. So what we've got here is we're going to do the modulator. And we're going to run it at a much lower frequency than we have so far with our sine waves. Times, what are you going to need? I'm going to call it modulator hertz. And the modulator will run for as long in sampled as the carrier does. Let's see, so what do we want our modulator to be? I'm going to say, in order to give something that's fairly easy to hear, I'm going to give it a period of a quarter second, which means it's going to be 0.25 hertz. So much, much, much lower in frequency there. So I'm going to go ahead and do something called modulated is equal to carrier times the modulator. And then I'm going to go ahead, move this comment here. So the same things still apply. I'm going to go ahead and attenuate the modulated carrier by 0.3 so it doesn't come out as a loud blast. But now I'm going to make something I call modulated ints. And that will be the same integers that we need to create our wave file, and I will call it amplitude modulated. So now the moment of truth. Let's go ahead and make the waveform, listen to it, and then look at it as well. So I'm going to run the script. There it is. It's written. I'm going to flip back to the Finder, grab amplitude modulated, going to open up with QuickTime. So you can kind of hear it fade in and out. Let's go back over to Audacity and take a look at what we made. So I'll import the file again. Or actually not the same file. Okay, so it already looks different. Looks like the amplitude still is maxing out at 0.3 and negative 0.3 there. But it's going up and down like this, and that's why you hear the fade in and out. Like that. So as you can tell, as we keep going in time here, the peaks of the waveforms just keep getting lower and lower and lower, then disappear, then going higher and higher and higher. But they really shouldn't be disappearing completely. And that's because I simplified the math really quick to make that AM waveform. Let's go back and make it so that the math works out even better. So at the point where the waveform is, the modulator is 0, that the carrier doesn't disappear completely. So let's construct an envelope, and a couple of things that we'll need to know before we do this is something known as amplitude sensitivity, which is abbreviated as Ka, and the carrier amplitude, which we'll call AC. So AC is our amplitude of the carrier, which we'll call 1.0, and then Ka is going to be the sensitivity, which we'll also call 1.0. Let's see how this works out in just a minute. So the envelope becomes AC times 1.0 plus the modulator times the sensitivity here. That is kind of a dense equation there. But what is going to happen is this Ka is going to increase how sensitive the carrier is to having its shape changed by the shape of the modulating signal. And so Let's go ahead and demonstrate this with a few experiments. Oops, one more thing. I need to change the carrier envelope to the, so it looks like so let's go ahead and hear what the results are with the amplitude carrier of 1 and the carrier sensitivity of 1. Flip back over to our finder. Okay, so it's still being pinched off at the end there, but let's try messing around with the carrier sensitivity. Sorry, before I was saying carrier sensitivity, I meant amplitude sensitivity. So let's go ahead and see what happens when our amplitude sensitivity is 1. So we've already heard it. Let's open it up in Audacity and take a look. So it's still getting pinched off here. That's at 1.0. Let's try dropping it. So flip back over here to Atom and make our amplitude sensitivity 0.5. So just half. Run it again. See if we change it in Audacity. Aha! Look at this. When the modulator reaches 0, now it just gets squeezed down a bit, but it doesn't disappear completely. So I wonder what this sounds like. Let's go ahead and change another setting. Let's go ahead and call it 0.25. Run it again. Import in Audacity again. And it's changed even less. And so there you go. There's how you modify it with the amplitude sensitivity on the carrier. Let's just review what I did for this amplitude modulation. So you probably, if you do your own experiments, you're not going to want to mess with that. Unless you want to change the sampling rate, which we really don't need to. But essentially made the carrier hertz of 440. I made a modulator of much lower frequency. You don't have to. You can experiment increasing the frequency. Try that out. I defined an amplitude of the carrier of 1.0. But most importantly, I need to create the amplitude sensitivity, abbreviated Ka. And if it's a 1.0, that is the maximum amplitude sensitivity that you should have. And that means that the modulating signal could potentially drop the whole modulated signal. So it would take the carrier and it would make it all 0, which you don't necessarily want. So you turn down this Ka so that the amplitude modulation has a lower effect. So once again, let's demonstrate that. So let's run this through 1.0, in which point it can be completely pinched down to 0. Let's go ahead and flip back here and do 0.5. Now it doesn't get pinched down all the way to 0, though it does change quite a bit. Let's finally look at 0.25. And at 0.25, it affects the carrier even less. So, pat yourself on the back. You've made it through a long-winded code walk-along. And this is really quite exciting, though. At least I think so, because it enables us to go just from straight beeps to something that actually starts to make some sound, have some movement, have some rhythm, have some life to it. And so, as we carry this forward, this work will actually pay great dividends in making our synthesized audio. So until next time, thanks for watching, and keep on synthesizing.